All right, welcome to part 2 of today's lecture, which is going to be on friction, and we'll also talk about drag, but moving forward, we're primarily going to be focusing on friction in this class, so that is the main focus. So we've already established that there are two types of friction, static friction and kinetic friction. So we want to get into more details on how these two different frictions work, because they do work a little bit differently. And we want to kind of just make sure we understand the difference between the two before we can get into the equations. So we need to talk really briefly about the cause of friction. So we know from our day-to-day lives, stuff has different textures, right? Some stuff is smooth, some stuff is rough, some stuff is even rougher. Other stuff can be even smoother. It all just depends on the application of the object. So for example, ideally your phone is going to be smoother than the road. Ideally, your hardwood floor or linoleum or whatever it is smoother than your carpet. So there are things that we want to be smooth and things we want to be rough. But even the stuff we think of as smooth, so it's smooth to the touch, it's not actually smooth if we go to the atomic level. So if we go down to looking at the actual atoms on the surface of our object, it's not going to be smooth. We're going to have these valleys and peaks in our surfaces that have, it's just nowhere close to smooth. And there's a couple of things that can happen that's going to result in our object having friction. So here we have a shoe on a hardwood floor, and there's a couple points where we actually have contact between the shoe and the floor. And where these points are contacting, there's a chance you can have a bond formed between the two materials. Now it might not be a strong bond, it could be a weak bond, but the bond forms nonetheless, and then you're going to have to break that for the object to move off the floor, so in this case the shoe. It's also completely valid if we look over on this right side here, the two peaks are caught on each other. So not only are you going to have to break bonds, but you're going to have to force the peak over if you're going to the left, or if you're going to the right, you're going to have a different experience. So this is what is causing friction to occur. The fact that stuff isn't atomically smooth and it's interacting with other non-atomically smooth objects, that is going to be the result or the cause of friction. So let's talk about static friction. So static friction is the force on an object that keeps it from slipping. So when we talked about static friction, we said that the object was at rest to the surface. And this can happen for any amount of time. It can happen for a short period of time. So for example, when you're walking or running, your shoe is with your foot that's down, it's at rest for however long your stride happens to be. So you would have static friction there. You could have something a little bit longer, like the dresser or some other large piece of furniture in your life, that it's there for a long period of time. Both have static friction being applied to them. So we're going to consider an example of a box on a string. And here, let's pretend this box is fairly heavy. So you can't move it as soon as you start trying to move it. It's going to take you some effort. So the direction of the static force is opposite to the pull, which is going to prevent our box from moving. So here static friction is preventing us from moving, so it would have to point to the left. That is the direction the static force would have to point in this given situation. Now, we can draw a free body diagram for this. So here we have the normal force, because it's on a surface, it's pointing perpendicular to the surface. Our force due to gravity points downward. Tension is pulling us to the right, And the static friction is pointing to the left to counteract the tension because we're not moving. Tells us the object is at rest. So that means in both the y and the x direction, we are going to have Newton's first law being applied. Because again, our object is at rest in that given direction. So the size of the static friction actually is going to depend on how hard you push or pull the object. So if you pull a little bit and the box doesn't move, you're not getting the full value of the static force. Because if your object's not moving, so it's not suddenly moving to the left, even though you're pulling it to the right. Right? The static force is perfectly balancing out the tension in the case of this box. It's perfectly balancing it out. So if you increase the tension a little bit, the static friction increases a little bit as well. Because again, you haven't put enough effort in, enough force in to move the object. So Newton's first law is still applied. So that means that the static friction value has to increase as you increase the tension as you pull on this box. Eventually, you are going to get to a maximum value where you can push or pull hard enough and you can overcome friction. This maximum value is given as such. So you have force of friction, or force of static friction, max is equal to mu s times n, where mu s is the coefficient of static friction and n is the normal force. Now the thing about our equation here for static friction is we're talking about the maximum value. So as soon as your force, in this case tension, is larger than static friction force maximum, you would start moving. And then you would need to change the type of friction we have because we're no longer stationary with respect to the surface. So this is the maximum value you can have. So if the static force or static friction is less than the maximum static friction, the object is not going to move. So in the case of this first one here, or even our free body diagram above, our object is not moving, so our static friction has to be less than the maximum value. If, oops, that should be S, not X. If the static friction is equal to the maximum object, the object is going to slip. It's going to start sliding with respect to the surface. So now the tension is high enough on this box such that we're able to move it in the direction we're pulling, in this case to the right. So with static friction, it has a maximum value. And you cannot be larger than the maximum value. I don't know what's going on with all these X's. They should be S's. So if the static friction is less than the maximum value, we have to be stationary. If we are at the maximum value, we're going to start moving with respect to our surface, and you cannot be above the maximum value. The static friction in which your object has to be stationary is never going to be larger than the maximum value. That's not how it works. So this here is our equation for the maximum static friction. This is typically the equation that we are going to be using when doing maximum or doing static friction equations, is we're typically going to be looking at the maximum case, as we'll see in the next two videos. So let's really quickly talk about the normal force and gravity. So this isn't explicitly in this section, it It assumes we've covered the incline stuff before, which we haven't yet. So I just want to really talk about how the normal force is not always the exact opposite of gravity. Because if we look at our equation for the maximum static force, we needed the force from the surface. We needed the normal force, right? We had F, oops. We had normal force, oops, US normal. So we need to make sure we know how to calculate the normal force because it's not always something that is going to be explicitly given to us. So far, what we've dealt with primarily is a nice box on a surface. So in this situation, we could draw the force due to gravity. Again, FG, MG, FG, any of these, whatever one you want to use. And perpendicular to the surface, we could have the normal force, whatever one you want to use. So in both of these, so in this situation, the normal force is the exact opposite as the force due to gravity. So our object is resting on top of a surface. That surface is pointing upwards. Gravity is pointing downwards. They're exact opposites. So in this case, normal force is the force due to gravity. But what about if I turn this 90 degrees? So now I have my object pushed up against a wall. Well, the definition for gravity was that it always points straight down. So gravity still points straight down. However, my normal force cannot point upwards. My normal force can't point up because that would be parallel to the surface, and it's called the normal force, the perpendicular force. So the way that the wall is supporting this particular box would be directly to the right. The normal force is pointing to the right in order to, it's not moving through the wall. It's staying up against the surface of the wall, so the normal force is going to have to point to the right in this case. So these are two extremes, right? Our surface is at 0 degrees or 90 degrees using a standard coordinate system. But what about if I'm on an incline? Well, if I'm on an incline, it doesn't matter. My force due to gravity still points straight down. My normal force, though, does not. My normal force needs to be perpendicular to the surface. So there's a difference. There's some angle between my normal force and the force due to gravity. So here we can see that they are not 180 degrees from each other. So do not get used to the idea that the normal force is just equal to mg, because I've just shown you two cases where it's not. So the normal force is something that we will need to make sure we are calculating correctly in order to go through and solve. Today in our, in the second video, so the first video, we're going to look at this nice horizontal surface. The second video, we're going to look at the vertical surface. And in our next lecture, we'll talk about an incline. But for now, just understand that the normal force is not always anti-parallel to gravity. All right, so let's talk about kinetic and rolling friction. So these are two other types of friction. We very rarely are going to be dealing with rolling friction, but I just wanted to very briefly mention it. So let's talk about kinetic first. So for kinetic friction, the two surfaces, so your surface, your big surface and your object, whatever they are in contact with for each other, those surfaces are sliding with respect to each other. So what is happening is the surfaces are not stationary. They are just sliding around some way, shape, or form. Now, with kinetic friction, it's a lot nicer because it's to deal with because it's nearly always a constant magnitude. So the force due to kinetic friction is equal to mu k, which is the coefficient of kinetic friction, times the normal force. And as we saw when we first talked about friction, this is going to point in the opposite direction of motion. So static friction pointed in the opposite direction the object would move. Kinetic friction points in the opposite direction the object is moving. So simply, we'll just take the coefficient of kinetic friction, whether that's given in the question or it's you have to look it up in table, I think it's 6.1, it might be 6.2. It's on the next slide. Just pull it from the table and we're good. Now, the kinetic friction force is going to be less than the force due to static friction. So if you think about trying to push a really heavy object, it takes you more force to start moving the object than it takes for the object to continue moving. This is because you don't have as much time for these surfaces to interact with each other and create bonds or get stuck in those imperfection divots. Now for rolling friction, this is a very specific type of static friction. So if we think about a tire that is rotating on a surface, part of the tire is actually stationary when it is rolling. So this bottom part here is stationary on the surface, and then the way that a tire moves is the next part becomes stationary to the next part of typically a road. So it's stationary for a brief moment in time. This is assuming you haven't locked your wheels and you are, doing inappropriate car tricks or, accidentally hydroplaning or anything like that. This is assuming a normal driving situation where your tires are rotating and they are static for a brief moment in time with it. So to calculate the rolling force, it looks exactly the same as the kinetic frictional force, except for R instead of K. But again, we're not going to be using it very often, if at all. So yeah, here's the equation for rolling friction. So we have F subscript R is equal to mu R, so the coefficient of rolling friction, multiplied by the normal force. So table 6.1 here has some standard coefficients of friction that you will, if the question does not explicitly give it to you, this is the table you should refer to. So if we look at our values, we can see that static friction, the coefficient of static friction is larger than the coefficient of kinetic friction, and those are both larger than the coefficient of rolling friction. So it is easier to roll an object in comparison to translating the object on a surface. This model here is a pretty nice model that kind of summarizes with how friction works out. So friction is going to be parallel to the surface because that is where it is coming from. And it's going to be related to the direction that it moves. So the static friction we said can change. So here we have a graph that shows that we have a linear increase in our static friction. We're going to get to the point where we're going to be able to move it. It drops down and then we move at the value for the kinetic friction, the force due to kinetic friction. So the equations, like I said, they all look pretty much the same. And we just need to make sure we're using the correct coefficient for which friction we happen to be using. So very briefly, I just want to talk about drag. I know we very briefly also talked about this with projectile motion, but I just want to talk about it again now that we've talked about forces a little bit more, so hopefully it makes a little more sense as to what the equation is talking about. So like friction, drag slows us down, sometimes also referred to as air resistance, because we are moving air molecules out of the way for the object to pass through. So the model, so we are not using the exact equation for drag. It's pretty complicated. You need simulations to accurately describe how it works out. So the model that the textbook is going to use, again, we're probably not going to be doing drag where we're calculating it out, simply because there's not really a lot of it in this textbook, and the questions that are associated with drag tend to be more difficult than those with just friction. So we're not going to be dealing with drag, but I want to talk about it again briefly. So with the drag equation, we are actually going to be making a couple of assumptions. First is that the object is moving near the Earth's surface. And again, near the Earth's surface is within a couple of kilometers of the Earth. And this does a couple of different things. First, it makes it so that the air density is roughly the same throughout all of it, because as we go up higher through the atmosphere, our air density changes, and that would change how our object moves. Our object can't be too small or too big, and the object can't be going too fast. If you're going too fast or it's too small or too big, you would need a different model to do drag simulations or equations. So the equation for drag is given as such. So we have the force due to drag. It's equal to 1/2 the drag coefficient, which you can find in table 6.19. Basically, we have 3 shapes and we have to guess what shape our object is kind of like. Multiplied by rho, which is the density of air, A, which is the area, the cross-sectional area of the object. Oops, that's from something else. And then V is the speed of our object. So the reason in this class we don't talk about drag very much is the force due to drag is something that is changing. And so because the force due to drag is changing, that means the acceleration due to drag is changing if we have a changing velocity value. And in this class, we are dealing with constant acceleration. So that is why drag typically isn't done very much in 129 or 130. If you were to go on to upper division classical mechanics, drag becomes a little bit more important there, but that is not this class. All right, so that's going to wrap it up for this video. The next 2 videos are examples of using friction in a couple of different situations, and so please make sure to watch those.